Let us look at second theorem of isomorphism. It says, let G be a group and H a subgroup of G and N be a normal subgroup of G. Then Hn is a subgroup of G. H intersection N is a normal subgroup of H. And there exists an isomorphism between H by H intersection N and Hn by N. Diagrammatically, this is what it means. H is a subgroup of G, N is a normal subgroup of G, Hn is a subgroup of G, H intersection N is a normal subgroup of H, then this isomorphism exists. Now, if we compare it with our first theorem, there we were talking of a isomorphism between a quotient group G by kernel of phi and the image of phi or phi, which was a subset of H. So here, what all do we have to prove to address this second theorem of isomorphism? If we compare these two diagrams, H is a subgroup of G. That means on its own, it forms a group. We have to show that H by H intersection N is equivalent to saying G by kernel of phi. So here, how can we do that? Now remember, kernel of phi is a normal subgroup and G is a group. So here, H is a group. We have to show that H intersection N is the kernel of phi. And here we have to show that Hn by N is equal to the image of phi. So let's take it step by step. Let's start off with Hn being a subgroup of G. We have to show that. So Hn is the union of all cosets Hn, where H is in H. Since N is normal, H1n, H2n is equal to H1, H2n. And inverse of elements of Hn lie in H inverse n coset, which also lies in the union Hn. The elements, the product of the elements lie in the union of Hn, and inverses also lie in the union of Hn, which implies Hn is a subgroup of G. Now we have to show H intersection N is a normal subgroup of H. So here, let phi or phi be the homomorphism between H and Hn by N, where phi of H is equal to Hn. Now here, Hn by N quotient group whose elements are the N cosets contained in Hn. H1 and H2 be in H. Then phi of H1, H2 is equal to H1, H2 times N, which is equal to H1 times N times H2 times N, which is equal to phi of H1 times phi of H2. So, which means that phi respects the group operations and hence is a group homomorphism. And what is kernel of phi? Kernel of phi is a set of all those elements of the subgroup H where Hn is equal to N, which is equal to the set of all those elements which are in H and they are in N, which is nothing but H intersection N. So kernel of phi is equal to H intersection N. And since kernel of a homomorphism is always a normal subgroup, we can say H intersection N is a normal subgroup of H. Since H intersection N is a normal subgroup of H, the quotient group H by H intersection N exists. So which means we can show it as a canonical projection pi, which maps H to the quotient group H by H intersection n. We show that image of phi is Hn by n quotient group. So an element of the quotient group Hn by n is an n coset of some element x in Hn. That is, we can write it as Xn. But any x in Hn can be written as x equal to Hn with h in h and n in n. Then Hn times n is equal to h times n, which is equal to Hn. So every coset in Hn by n is of the form Hn for some h in h, which implies image of phi is equal to Hn by n. That means psi is subjective. Okay. Now, what all do we have? We have shown that Hn is a subgroup of G, that H intersection n is equal to the kernel of phi. That means the quotient group H by H intersection n is a quotient group which exists, and which means pi exists. And we have shown that Hn by n is a image of phi. So our first isomorphism theorem then guarantees us that this isomorphism exists. How? So let's see. H is a subgroup of G, implies H forms a group on its own. Kernel of phi is equal to H intersection n. Image of phi is equal to Hn by n. So let's bring in that diagram again of the first isomorphism theorem. So H forms a group. Image of phi is Hn by n. Kernel of phi is equal to H intersection n. So that means this quotient group exists, H by H intersection n. So we can say by doing the necessary substitutions that H by H intersection n quotient group is isomorphic to Hn by n quotient group. Now let's look at this theorem using an example. Let's take G as the group formed by Z sub 24. That is the set of integers 0 to 23 under addition modulo 24. Now let's look at the elements and subgroups. Let's take a subgroup of G as H. So let's take H as the subgroup generated by 4, which is 0, 4, 8, 12, 16, 20. And the order of this is 6. Let's take a normal subgroup N generated by 6, which is equal to 0, 6, 12, and 18. And the order of this normal subgroup is 4. One thing you should be clear about is that in a cyclic group, H and N both are normal. So here, H being normal doesn't matter. What matters is N is normal. So H intersection is what? H is this, N is this. So what is common? 0 is common and 12 is common. So H intersection N is equal to 0, 12. And the order of that is 2. Hn is a group subgroup generated by H and N. That is generated by 6, 4. In Z24, this is the GCD of 4, 6. The generator is GCD of 4, 6. GCD of 4, 6 is 2. So the subgroup generated by 2 is the subgroup generated by Hn. So 2 generates Hn as 0, 2, 4, 6, 8, 10, 12, all the even numbers. And the order of that is 12. Now let's form the quotient groups. Cosets formed by H intersection N are these. So 0 plus 0, 0, 0 plus 12, 12. So 0, 12 is generated by 0 from H and all the elements of H intersection N. Then we take 4 from H and we add it to all the elements of H intersection N. So 4 plus 0 is 4, 4 plus 12 is 16. And if we keep repeating that for all the elements of H, we get these cosets. Now, here if you notice that 0, 12, 12, 0. In set notation, they are the same. 4, 16, 16, 20, 8, 8, 20. So there are repetitions. So the unique cosets formed by the quotient group H by H intersection N is 0, 12, 4, 16, and 8, 20. Now, similarly, unique cosets found by Hn by N are 0. Hn is what? Here, Hn is this, and N is 0, 6, 12, 18. So let's start off 0 plus 0, 0 plus 6, 0 plus 12, 0 plus 18. So 0 plus N gives us this. Then we take the next one. 2 plus 0, 2. 2 plus 6, 8. 2 plus 12, 14. And 2 plus 18 is 20. Then next one, 4. 4 plus 0 is 4. 4 plus 6 is 10. 4 plus 12 is 16. 4 plus 18 is 22. Now, we don't really have to go through all the cosets. Look at this. 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. All the elements are covered. All the elements of Hn are there in any one of these sets. So that means whatever we get further as we go along will be a permutation of these. So these are the 3 unique cosets formed by Hn by N. So unique cosets formed by Hn by N are 0, 6, 12, 18, 2, 8, 14, 20, 4, 10, 16, 20. Now notice that each Hn by N is a subset of Hn. So this is a subset of Hn. This is a subset of Hn. This is a subset of Hn. So now we can define a homomorphism psi from the quotient group H by H intersection N to Hn by N, where psi of H plus H intersection N is equal to H plus N. Look at the orders. Order of the quotient group H by H intersection N is 3, and the order of Hn by N quotient group is 3. Looks promising. So now, if we verify this psi, how do we do that? Let's take H equal to 0. 0 plus H intersection N is equal to 0, 12. We have formed these cosets. And psi of 0 plus H intersection N is equal to 0 plus N, which is 0, 6, 12, 18. If we take H equal to 4, 4 plus H intersection N is 4, 16. And psi of 4 plus H intersection N is equal to 4 plus N, which is equal to 4, 10, 16, 22. Like that, we form or we verify psi. Again, you will notice there are repetitions. So the one-to-one mappings are 0, 12 to 0, 6, 12, 18, which is equal to 0 plus 1. Similarly, 4, 16 maps to 4, 10, 16, 22, which is equal to 4 plus n. And 8, 20 maps to 2, 8, 14, 20, which is equal to 2 plus n. All the others are repetitions. So the mappings are consistent, which implies psi is well defined. So psi is an isomorphism, and h by h intersection n is isomorphic to hn by n. Now, how did we get this? By applying the first isomorphism theorem. So that was second theorem of isomorphism. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.